that has an amplitude of P. So how about we call that amplitude something like R? So R is going to stand for reflection coefficient. And you can imagine that the amplitude is going to be based on how much of this incident wave is going to get reflected once it hits this interface. So we can actually write our equation in the following form. We're going to have EIK1x plus RE minus IK1x. So that's it. We just actually found two constants, two arbitrary constants, simply by using some physical reasoning. We didn't have to apply any boundary conditions to find this. We chose it for the problem at hand. Now, to find this actual coefficient, we will need to do some more stuff. But before we do that, we need to define the function in the second region. So now we're going to have the following. The Schrödinger equation in the second region is going to be the following. It's going to be written as follows.
Hi, I'm Dr. Killen. I have my own medical practice, and I've been using Doodly now for a few weeks.
Now we know potential is going to have a finite value, a non-zero value of V naught. So we need to include that here into the Schrödinger equation. There's just no way around it. And this is going to have a very interesting effect on our solution. Because we can essentially write this in the following way. We can write psi double prime 2x plus k2 squared psi 2x equals to 0. If we make k2 equals to the square root of 2m times e to the minus v naught over h bar squared. And you might notice that this is actually going to be a little bit more complicated to analyze because, as you can see from here, the energy of the particle is actually going to affect its behavior in this second region. So we're going to have to analyze the behavior of the particle based on three cases. We have the case in which the energy is greater than the potential, the case in which the energy is less than the potential, is equal to the potential. So that's something that we will do as well. Now, before we move on to analyzing those three cases, I want to write the general solution to this equation here in the following way. We're going to have some other constants e to the I k2x plus some other constant d e to the minus I k2x. And you'll notice something very peculiar about this. This, once again, represents a forwards propagating wave, and this represents a backwards propagating wave. So let's look at the problem at hand once again. If this incident wave gets transmitted through the potential span, then do we really have any backwards propagating wave here? Because in essence, something propagating backwards from here, we would need something to get reflected here. But we know that this potential is just going to stay constant at the value v naught to infinity. So there's never going to be another interface from which this is going to get reflected. So the only logical solution to this problem here is to make the constant d equals to 0. Because there is no way from a physical point of view that we can have a propagating wave inside that potential, or basically for x is greater than 0. And the other thing that we can say is, well, if this is going to be the transmit wave, then why don't we just call c something like the transmission coefficient, such that conservation energy is retained? We're going to have incident energy plus reflected energy equals to transmitted energy. So we can rewrite our solution in the following way. We can write t e to the I k2x. And this is basically it. So now we have the solution for both regions. And now all we need to do to solve this is to actually just find boundary conditions. So that is basically what we're going to do now. We're going to find out what the boundary conditions are going to be. So let me just make some room for that. And let's clean this space here. Okay, so let's see what the boundary conditions will be. Well, we need to think about this more critically than before because they're not going to be so obvious. Now, the boundary conditions will be given by this interface here. We know that there needs to be conservation of energy. So that means that our waves essentially at this point is going to be equal to the wave at this point. And this is not because of conservation, but rather because of continuity of the function. Remember, if we have a continuous function, imagine that this is our wave coming in here, and then it happens to form here. Well, the wave cannot just abruptly just jump here and then start here. We need to have continuity. So this point has to be connected with this. So the value of the function needs to be the same for both of them at this point in which they're both connected. This is just a physical kind of condition that we need to meet. Otherwise, it just wouldn't make sense. What actually happened to the wave here, we wouldn't be able to explain that. So we need to make this condition. Now, the next condition is going to be, well, imagine that your wave is coming in this way, and then it changes to something else. What you notice here is that the gradient needs to be the same for both because it is essentially the same point. So from analysis, we can conclude that the first derivative at the x equals to 0 needs to be the same for both of these.
Grammarly errors. With Grammarly, you can find really good, no, perfect words.
So now what we're going to do is we're going to make this equal, and we're going to solve for the constants r and t. So let's start with the first equation. First equation is going to give us the following. We're going to have e to the ik1 0 plus r to the ik1 0 equals to t e to the ik1 0. Now this is going to become 1, this is going to be 1, and this is going to be 1. So this equation in the form 1 plus r equals t. And you'll note that, well, that sort of makes sense because we expect reflectance and transmittance to add up to 1 because there are no losses in the system. So conservation of energy tells you that they should be the same. Now, see, there might be an inconsistency in the way that we define the sign here, because obviously when we add up transmittance and reflectance, we should get 1. But this, remember, these are coefficients, not necessarily the total reflectance and transmittance. So this is something that we investigate a little bit later on. That's what the first equation gives us. And now the second equation is going to give us the following. The first equation is going to differentiate into the following. EIK1 0. And then this is going to be, remember this is minus here. So this now is going to be minus ik1 r times e to the minus ik1 0 equals to ik2. I forget that this was a k2 here. T e to ik2 0. So this is 1, this is 1, and this is 1 again. And now what we're left with is, well, the i's are just going to cancel out. So we can get rid of those. We're going to be left with K1 minus K1R equals to K2 times T. And if we solve for T, so basically just put this in here, we're going to get 1 plus R times K2. And then if we expand this becomes K2 plus K2R. And then we just rearrange to solve for R on both sides. So this implies that R have the following value, K1 minus K2 over K1 plus K2. And then T is just going to be 1 to K1 over K1 plus K2. And this is basically what we're going to get for reflection and transmission coefficients. Now, in the next video, we're actually going to go a little bit further than this. Even though this is technically solved, we need to investigate what happens physically when the energy of the particle shifts about the constant value that the potential step has. And we're also going to find out how to calculate the total reflectance and transmittance of this system based on these two quantities.
So, welcome back, guys. Just a moment. I think we've cancelled out the interference. So yeah, today we're going to be looking at the potential steps. So I just wanted you guys to get some sort of introduction to it. So just go through it one more time, and then we'll go through the reasoning and then the solution. So also that has given me time to admit the rest of you who are coming in one by one. Jimmy, Kwezi, Were Henry, Every Wycliffe, Emmanuel Otekayot, Maweje David, Israel, Kalimba Ian Kennedy, Keith Membe, Nambi Swabra. You guys are welcome. Isaac Waligo, Mwanja Charles, Biso Godfrey, Agarie Thonapa Ambrose, Ronela Nambi, Aman Meli, Kutosi Robert, Edgar Roleta. It's a bit new. Catherine Nambuga, Dodo Faruko, and the all caps man, Mutegechi Rogers. So what we're going to be doing now is we're going to go to the PDF. Just a moment. A minute actually. So let's just have that minute as we go back to the top of this PDF and get Iceberg open as well. And to the last university physics. So we're going to be looking at those solutions. We'll primarily use the notes mostly because there are different notations, but there are things also we need to look at in these solutions. So we'll have to refer to this. So let me just have them open. The timer is not changing. Depends when I go out, but it won't be more than a minute anyway. So it's So we are back here. Let me just take you through so that you can see where it is. So that would be chapter 5. Sorry about that. We do that. Okay, I hope there's no feedback. Let me just remove the sound. Now, so we have this in chapter 5, which is basically what I've looked at. Let me just zoom in for this one. Maybe fit to page. No. Okay, it doesn't want. So we saw the plausibility leading to Schrodinger equation. We have sort of looked at Bond's interpretation, expectation values, not so much. But we're going to have a look. We looked at the required properties of eigenfunctions, that they must be finite, single-valued, and continuous. And their first derivatives also must be finite, single-valued, and continuous. So also going to look at quantization when you have the confined particle. So most of this is the derivation, and it actually has one of the shorter derivations using the conservation of energy over there. Let me see if I can comment in this. P squared over 2m, then they define the potential, and then F is equal to negative dV dx, and then use the de Broglie relationship, lambda is h over p, and then Planck's V is equal to E over h. Sorry about that. Let's answer first. So yeah, you have K in terms of lambda and omega, E in terms of omega. So that's E in terms of omega. We already looked at this. Sorry, the pencil changed. So E in terms of omega, then getting from lambda, that moment, that de Broglie relationship to K. I thought it was a mistake, but so they first represent the constants by alpha and beta. And then go on to solve them using just the sinusoids. Remember, for the other bit, we're using exponents. But it comes up to the same thing, so where is it? That is using operators? No, they're just using constants there, so they end up with this version of the Schrodinger equation, which is what we had, the time-dependent Schrodinger equation. And so it satisfies all the assumptions concerning the quantum wave equation. And what are those assumptions? that you have the conservation of energy. One, that it must be consistent with the de Broglie and Einstein postulates. Then it must be consistent with this equation, which is the conservation of energy. Then the other ones we looked at as it must be linear in phi, and so the derivatives, and then we looked at this under conditions of solving Schrodinger's equation. So linear combination, and then the potential energy is generally a function of position and sometimes T. However, okay, those were the four conditions in case they are not obvious about that. So those four conditions help us with the plausibility of deriving the Schrodinger equation. So those conditions must be met. The conservation of energy, the de Broglie and Einstein relationships, the definition or what we expect the wave function to behave like, and then the existence of representation of those forces on the wave or particle as potentials V. So that is just the definition of V in some texts. And then that is Max Born. We have looked at that extensively. We already looked at all this, apart from the expectation, but I didn't use that approach. But we looked at total probability, and then this should be the particle in a box. No, these are the operators. We looked at that, but we didn't go into the details. So, okay, time independent Schrodinger, time independent. So this you need to know finite single valued continuous, and so must the first derivatives. So these first derivatives are going to be shown by the psi and the prime. So that is the first derivative, then this will just be psi. If you have a second derivative, it will be psi double prime. We looked at what single valued means and finite. We don't want to go into this now, but we want to go into the solutions. Right. We are really not doing the normalization first. So then we looked at solutions. So we looked at zero potential when the particle is free. And then today we're looking at the step potential. Energy less than the step height is less than V naught. And then we see E is greater than V naught, which has been in that video tutorial. And then the potential barrier is a combination of these two, really. Of that, and that. Of the potential barrier, which we'll also look at. Then we look at the simple harmonic, and then the infinite square well. Now, it's important to read through this text. Much as we've been talking about it. So maybe just to come back to the free particle, you had the cosine and sine. So sometimes you just have general constants here, A and then B. So this B includes the I in itself. And then that is sometimes given by that. So this A is not the same as this A. So we use that A and this A a bit different, actually. They're not just a bit different. But so in this case, the coefficients is just two coefficients. So sometimes you'll see IA, sometimes you'll see B. But that is what you have there. So these two, if you have A and IA, yeah, because that is an expansion of this. If you just have A and B, then they might be different. Now, we are going to be representing momentum by, you had a half mv squared. No? E is equal to a half mv squared, right? 1/2 of mv squared. And then P is equal to mv. Just in case there was somebody sleeping, you can just multiply through by V that side and then divide by 2. So this side equals to this side. So E is equal to what? Do you multiply through by V? No, that would just not be right. Okay, we square this. So it gives mv squared. So you see that we need to multiply by m here and by 2. So we need to also multiply this side by 2m. And so you can equate this, that P is equal to, okay, this will be P squared. P squared is equal to twice ME. So to get P alone, we take the square root of this, just in case somebody needs to go through it. So that's where we have that. So divided by H, that's where you see that thing. So do not be tempted to have this like that, unless you're going to put H squared here. So that is, sometimes people make that mistake. So if you're going to put the root over the whole thing, you'll have to square H. Let me check the charts briefly. It's relatively quiet. Okay. So that is where we get our K from. Then, of course, we ignore the time-dependent part. We are mostly considering time-independent solutions. Sorry about that. We looked at the conditions for K last time, and how there are only 3 solutions that you can have from that differential equation. So we looked at K positive, K negative. Now, much as it is important to look at, iceberg is just showing a possible condition where you have this this bit. So sometimes this is a cylinder. So you have the potential in here, and then the electron is just moving through this into that potential, and then you want to see that wave function. But since we have already had that tutorial, we'll first do something else. So again, this is those solutions there, A and B. Most of these solutions closely follow what you have in iceberg. So let's first do something else. That is when your energy is greater than the height, we are going to see something interesting about that as well, which wasn't apparent in the video. Then we are going to see tunneling, which is the potential step. But let's first go to the well, the potential well. So iceberg also gives you like what you guys call real world applications. Is what a potential step would look like, what tunneling would look like. Tunneling, you guys use tunneling all the time. You find out where, but okay, we're going to look at a square well and atoms. I mean, once an electron in on an atom, you guys have this planetary model. It's something like this. Then you have the electron somewhere there. Well, as comforting as that is, we have a three-dimensional model of the atom, so that even this stuff where you have those different circles for the atom, it doesn't really work. So what do we actually have? When atoms come together, these circles here, part of their wave functions overlap. So you have these wave functions here overlapping. So they form what are called wells. So you guys these days don't know what a well is. So now the electron exists in this well. And then it is trapped in this well. So sometimes they'll join up in this well, these levels. So at the top you have more. So all these energy levels will exist in this well. You can shade this side. And just is there like an eraser? Now, depending on the amount of energy required, then you have these wells quite deep, and then they are so so you have this electron trapped in that well, and so every time it so I can now illustrate the energy levels. Of course, towards the top, these levels are closer, and then here they are a bit more spaced. So we can call that E1. That won't be E1, maybe like E2, E3. Then when that electron is above here, you have a continuum of these energy levels. So to the electron, that is infinity when it's free. And then this is your electron. So the electron is trapped up within that well. So that's not a very good figure geometrically. So what we do is that we represent that well by just a straight line like that. So you have your electron somewhere there. It could be anywhere within that well, but it is in there. So that is what we have there. So we have that geometric equivalence. Of course, we lose some bit of the edges, but it is negligible. We no longer go into the details of the Brillouin approximations, and the Brillouin zones, but yeah, that is your square well. Maybe to just tell you what guys Brillouin is you have zones within the atom where you define those different energy levels. And these energy levels, remember the SPDF, those shells. So the S is the lowest and the number of electrons is 2. So we can see how those come about using Schrödinger theory. Sorry. But as said, we no longer go into that detail. We used to go into it when we had 2 materials courses. That is really what happens. but we're usually just interested in one atom. So these wells are much deeper, and as you have more atoms, then so that is why you have electrons much easily able to move between metals. So again, we also don't go into that bit, but these functions keep reducing as you have more ions, as you have more atoms. So essentially, in metals, maybe I can just talk about it quite briefly. You have the electrons belong to each of these atoms, but they are free to move from atom to atom. So that is why you have easily conduction. I think it's even there somewhere. So those are what you call the conduction electron. And of course, this whole bit here, since electrons are free to move, is what will be a conduction band. And then the ones below this side will be your valency band. At least you did that in physical electronics. So the free ones are in the conduction band. Of course, you see that they are still within the constraint, but they can move quite easily. And then the bound ones are bound to each of these atoms. So each of these hills here is an atom. Maybe that should help you with the applications of Schrödinger equation. So do we need to do something about this? Okay, there's a general look at it. So then the infinite square well, we'll not look at it from iceberg though. Look at it from university physics. So we'll try and cut out a bit of the detail. You guys will come back here and read through the detail. So we'll go to Young. And then you look at, it's actually what they begin with before they go to these barriers. Is it? I think so. I think so. Particle in a box. Yeah, after deriving this Schrödinger equation, they go to particle in a box. So, of course, we already know what those are by now. So these are time-independent functions. Do we need a pencil? And then that's the energy. So we're going to see what a state is now. Not like the one you're in, but remember those energy levels. So each of those energy levels correspond to a state. The ones we have been looking at previously in iceberg. So that is a state, and we already looked at those states in terms of okay, a bit. If you remember what we did under the spectral line, so each of those energy levels is a state. Now I have the time independent Schrödinger equation, but they have it slightly. Oh no, they're not the ones who. So the wave particle is the same. I mean, the wave packet is the same in both derivations, but of course, now for a free particle, you have this, and you already know where this comes from. And for that free particle, the wave function is given by what? By just an exponential function, jkx. And you know that this is a cos theta plus b sine theta. Okay, you can't see the cos and what, but just know it is there. Plus b s theta. Okay, that is your cosine and cosine. So for every particle, E is given by h bar squared k squared over 2m. And it's actually very easy to plot this energy E versus K. Is going to be something like this. So we can guess that is K, the K axis. Okay, let me not get carried away, but that's the E. That plot is significant later on when we're looking at how energy levels come about. Right? So we're going to see a particle constrained to a box. So it can bounce along these walls and gain different energies, but it's still within the box. Now these potentials that keep it are indicated by that V. So these are, so you imagine like a, okay, for now you can imagine walls, but so the electron bounces along those walls. So those walls keep it bound there, much like how you keep antimatter between magnetic fields. So it can't, technically it doesn't, classically it doesn't reach this wall because the repulsion is too great. But we have simplified this sort of curve to just a straight line. So if that electron is bound, we have the x-axis. So this is the origin, and that is L, which is the what you call the dimension of the well. So for the infinite well, you have those potentials tending to infinity, yeah? And we are going to see why they're important. So now, if this electrode is bound and you have levels, that means for it to exist, you're going to have those modes. Yeah, we are back to the modes. Let's go without. So you'll just have traveling stationary waves, and that is the only condition you can have for a wave within this confined space. The confined space places restrictions such that you have only standing waves which are able to exist. So one is, so that is intuitively, you know that there will be standing waves. So we're going to see what happens at this boundary and that boundary later on. But let's first look at our wave function. So in this case, so in between, okay, at the boundaries, at the walls themselves, V is equal to infinity. So that is not a contradiction because we said the electron really doesn't reach the walls. Of course, if it somehow gained enough energy, it would move to this side. But we say it can't gain enough energy to come. Actually, the picture is more like that classical. If you have seen guys doing high jump, so this is an infinite, goes all the way up, all the way up. So the electron can't get enough energy to jump over. So if in case like a pole vaulter, it will be jumping and then coming back. But let's say this wall here is not at infinity. So what happens that if you've seen those movies, those like horror movies, imagine a world where you can put your hand through. So if it's not infinity, we haven't yet looked at tunneling. I don't hide anything. Okay, screen maybe. Oh, that sucks. There's no zoom. We need that zoom. So in real life, though, okay, not in real life, the best analogy of these potentials is, you imagine something elastic. So the higher the potential, that won't bend at all. And then if the potential is low, then it's like those stretchy bands. So you can, like, the electron is sort of pushes through. So it moves beyond that axis to this side and then comes back. If the potential is not infinite. But we're going to look at the tunneling there. So that is so you have the electrode some distance away from. So it's more like a stretchy surface, and the higher the potential, the more rigid it will become. That is important to have that picture. So you won't find that in these books anyway. Maybe iceberg, I don't know. So you have your free particle. All the explanations are there in terms of the standing waves as well. So here already they are putting in the boundary conditions, but for one, we know that our wave function is going to be two waves. Now, this other one is sufficient for the free wave, for the free particle. But on this axis, how do we represent the standing wave, the part? So how do you represent? So you have the wave coming in that direction, and going in that direction. So these two waves are the stationary waves. They are still sinusoidal like this. That one you can, the solid one, you can take it as going to that side, and then the dotted line going to this side. So you have standing waves at these nodes. Now you represent one by the one which increases with x by this one, and then the one which decreases by that one. Now, there are no restrictions on this wave function because we know that it is confined to these walls, it is infinite. So the maximum value is x is equal to, let's use paint. No, let's not use paint yet. Let's. So you have x is equal to 0. Okay. I sometimes want to use paint. And x is equal to L. So we're going to, so first of all, we are using the properties we know already about what happens in a cavity to assume that the wave function is given by A1 kx and A2 negative k1x. Now, this background information is very important for these solutions of the Schrodinger equation. But before we have that as well, we can go back to what we already know as our solutions. So let's just go back to our solutions. So remember, we said that this is our K. And it was eta K squared, right? Now, so this E, once it, usually this is that is usually negative there. So You just have to correct that bit anyway. But the Schrodinger equation usually starts with the negative if these functions are positive. So if we multiply through, so that k squared is going to be equal to twice e minus v. So it's always going to be e minus v. But in this case, our potential is infinity, and we are going to see that, okay, if we include it in this bit, the boundary, sorry about that, we are not yet at the boundary. Okay, what we do is the region. That be a little confusing. So in between here, the potential is equal to 0, so V is equal to 0. So that's how you have this k squared. It's just twice ME. So you have your region 1, region 2, and then region 3. So Iceberg tries to put the axis here so that you can justify the negative x and the positive x, but it doesn't really matter. It just makes your solution a bit complex. The more intuitive will be having those standing waves. This is the one traveling in this direction, and then it's a bit the one traveling in that direction, and then the one traveling in this direction. So we saw that when our k squared is positive, will it be positive? Because it is e minus v, and our v is in this case 0. So e minus 0. So no, it is negative. E minus v. Yeah. If you multiply through, this will become negative 2, so it will become this side. It's going to be positive, so you'll have this cos and sine, but then we said that this is the same as AE I k x minus omega t. I'm supposed to put the brackets. Okay. So we said that is your wave function. Of course, that we are interested in the kx part of it. So this will just give you one solution. That is why we need to add the second one, the negative e negative I k. So this one I want to bother to include the time, because you know that the time is just a product of these two. So that is how you have these solutions. So sometimes it's given by another A, sometimes given by B, but let's just use A because this amplitude should be the same for the standing wave. So back to here. So our boundary conditions become important. So now we are looking at x is equal to 0. So that means we substitute for 0 in there. So AEIK 0, and that we also substitute 0. So in this case, this has been expanded out for you, so that the sine zeros are going to be 0. and then cos 0 is going to be 1. So, okay, this is grouping like terms. So at x is equal to 0, epsilon is going to be equal to 0, right? Should we go to paint? Guys, if you're not following, just let me know in case you need more explanation in the chat. Okay, I think you guys are able to follow from here. I don't see nothing in the chat. I don't see anything in the chat. So so those will this okay, after grouping, that will be equal to 0. And so you have that is going to be equal to 1 cos kx 0. So you have a1 plus a2 is equal to 0. That means a2 is equal to negative a1. What does that mean? Again, you saw that when this amplitude here goes like that, the opposite direction goes like that. So you have a1, then you have a2. So let's just have this as solid wave. And then that moves through there. So a2 is the dotted part. A1 is the solid part. So that doesn't contradict anything. And so you'll end up with something interesting for 4.27. You just substitute for that. So you saw this as so a1 plus a2. That means this cosine bit becomes like 0 because now a2 is negative a1. So you have that 2a twice I sine kx. So the wave function will be given by c a1 sine kx, where c is this coefficient. So in this case, we have been able to get this wave function by just analyzing this equation. Let's check the charts. Everything is there. Network is there. The people are there. So now, this is where the solutions become interesting. So we're going to get the derivative now of this. Shall we get the derivative? What does it tell us about okay, then the other condition is that the wave function is equal to 0 at those bits. Okay, we're going to explain that as well. But now we know that the wave function is 0 in these bits. And why is that so? We are going back to the pole volta. Oh, good. So in those two regions, epsilon is equal to 0 because we are saying these are infinite potentials. So there's no way this electron is able to jump over these potentials. There's not enough pole vaulting. They don't have enough energy to jump over this. So they will function outside this 0. And then the other bit, so now we know that the this function has to be continuous. So the value at this wall must be the same value going into this side. So we don't know what happens exactly, but all we know is that the value on this side must be equal to the value on that side. You remember from the earlier video, but also from what we discussed in the last lecture. So that is why epsilon is equal to 0 at this boundary and epsilon is equal to 0 at this boundary also. So we will scroll down. Where is this the equation? It is over here. Okay. So now epsilon is going to be 0 at x is equal to L and at x is equal to 0. Right. And so the derivative, but we need the derivative because if you differentiate this, you get cos. We don't need the derivative now. So since that wave function is going to be equal to 0 at those points, we can have a general C epsilon. We are going to skip the x is equal to C C K N X. So we have just introduced an N because each of these standing waves is valid. Sorry to pass. Okay, not sorry. We don't need to apologize for it. What are we saying? That for all these standing waves to exist, they are going to be differentiated by their number L, and we are going to see how, but let's first introduce it here because we have different standing waves. And so K is, you remember K is 2 pi over lambda, right? And then so we can express okay, maybe the derivative. Okay, because this is not making sense as it is of why epsilon is equal to 0. But if we equate this to 0, so we already know that C is not 0. So C is not 0. That means sine K. C. No, it's possible to paint. Oops. I'm separating in this bit. Oh, people who have been waiting, I switched off the volume. So let's first stop this and go to paint. So Right. What being good. So quality suffers usually. Anyway, it has already suffered. Okay, we'll use this other side. So f psi, f psi is going to be equal to c sine k n x. So now we have not put this side, this n this side, because it's going to be a bit funny. And we know that phi is equal to 0 at x is equal to 0, x is equal to L. Some people say L, L, what? It's one of the interesting letters people pronounce. So now what do we have? So we know that c is not equal to 0 because you have already seen that value of c here. It's definitely not 0. So therefore, sine x sine k n x is equal to 0. And that means knx is equal to arc sine of 0. Sine of 0. What's arc sine of 0? It's just 0 and then 2 pi. So it's magnitudes of 2 pi. So when n is equal to 0, that's when n is equal to 2 pi, which is 360. Should have a sharp circle. So that is 0, and then that is 360. So 360 in radian is 2 pi. So okay, we're sort of trying to introduce the n there, but kx is equal to 2 pi n. So what do we need? K's or x? We need solutions of x was 0. So at x is equal to 0, we don't get a lot of information because that x is going to be equal to 0. So let me not cross it out now. So we get more information when x is equal to L, such that KL is equal to 2 pi, and that second boundary. That therefore means that K is going to be 2 pi n over L. So we can write our solution as f psi is equal to C 2 sine 2 pi n x over L. So I think we can first eliminate this n now. Let's try to use it to, but you can still get it intuitively. Let's eliminate it for now. So we have this other bit for, let me just zoom out briefly. It's already a big canvas. So we don't need to make, let's remove this bit. So that is our general equation for psi. Let's just make sure it is clear. No, we need a pencil. Let's just put a rectangle. May nobody have time to draw. So that's our wave function. And we have said that k is equal to n pi. So k itself, which is 2 pi over k, 2 pi over lambda, over lambda. So we're going to see that these waves are going to exist in multiples of L, because lambda is going to be L over N, and that looks like the standing wave condition. So your wave function is going to be an integral multiple of L. But that's not really the exciting bit. Let's first go to Kaisberg and I'll just get what we need from there. Okay, next we're going to look at but we haven't used the derivative. I think we'll use the derivative once we're finding. Geez, we haven't used. Okay. Now we know from De Broglie nobody got time for that. From the De Broglie hypothesis, lambda is equal to that. Lambda is equal to h over p, right? We can get p by p is equal to h over lambda, right? So here we're trying to get energy levels. Try to get energy levels. So, and so our lambda is L over N. So P is going to be equal to H divided by lambda, which is L over N. So 1 over lambda is typically N over L, NH over L. And then we also said that, what else did we say? Wait. Okay, for some of the texts where you have where they just give k as 1 over L, 1 over lambda, you'll have a 2 somewhere, but so why is there? Just a moment, I need to see why there's a 2. Oh, okay. So sorry about that bit. Sign also repeats every, even this 180 is a negative 180 is also 0. So by multiplying through by 2, we had not considered that. Right. So that is where you have KL is equal to n pi. So that 2 will also go. That means even our equation doesn't have the 2 in it. So it's just pi nx over L. Let me also delete this now. 2. Yep. Where? So our k is going to be given by 2 pi over lambda. So lambda is, so that pi goes, and then there's going to be a 2 here. There's going to be a 2 over there. So there's going to be a 2 there. Now we know that E is equal to P square over 2M. So let's just scroll down. So if we substitute for P there, we'll have N H why isn't that H quantized? Did we make a mistake somewhere? No, we did. To be N squared, H squared over 2M times. So what's 2L squared? That becomes 4L squared, right? Okay, let's just say 2L squared, which is NH, N squared, H squared over 8 ML squared. So we know that your E is that. So sometimes you just divide through by 2 pi. And that will give you N squared H bar prime squared over pi squared over 2ml squared, or NH squared over 8 ml squared. So you have those two expressions for your energy, and they are both valid. And this, you can see, very closely relates to what we had from the Bohr atom. So we have a few minutes. Yeah. So this very closely relates to what you had for the Bohr atom. So it's important to add that the restrictions on n, so n is equal to, well, 0 doesn't make sense. That is just a free particle. So you can start from, well, you can also include it there, but it doesn't make sense. So we have 1, 2, 3, and so on. And this will give us what we call our quantum numbers. And from that will give us the quantum numbers. And quantum numbers are used to indicate among the things, the number of electrons in the well. Then the last bit is what we want to look at, normalization of that wave function. Let me just share this from. Just having this over here. No. Some people think let's proceed it to it. So the same way you had the energy levels. So I think I was a bit more aggressive with the cutting. So that is n is equal to 1, n is equal to 2, n is equal to 3, etc. And so these are the resultant waves that you have. When n is equal to 1, you can substitute back from your sine. What was that equation again? Sine n pi x n pi n x. So when n is equal to 1, you have n sine pi over L, and so we need to first normalize this. But that is your first wave, and then second wave, 1 node, 2 nodes, 3 nodes, etc. So you just know it's 0 here, 0 here. When x is equal to L, it has just made 180 degrees. Okay, you can still plot it because here x will be L, so it just makes 180 degrees. It doesn't. So when n is equal to 2, it has made 360 degrees. So that is. So every time this moves out, you have, every time it rotates, you have a wave. You have, imagine a point on a circle starting at 0. So it has moved 180 degrees, that's where it is. It has moved 360, that's where it is. More than 360, that's where it is. It is, so that's how you're able to get this by rotating this circle here to see where your wave has moved. And these are standing waves, of course. There's a corresponding wave in this direction. So it just travels back along this line. These are the standing waves. No, that was in our initial assumption, but ended up with this just C of that. So we just saw that there are going to be waves like this. There's actually, that red wave is not there. It just propagates back along the same line. But the concept is there. What else we need to know about this? How comes we have not done normalization? Okay, we'll use the remaining minutes to do normalization. So normalization will give us the value of C, right? We know from Max Born can normalize the wave function to give the value of C. From the Max Born interpretation of the wave function. So what we do their function? Oh, okay. Don't worry about the spelling. So we know from the Max Born interpretation that, of course, this is psi times that gives you the probability of finding the wave. Probability of finding the particle within the wave. So we know that if we integrate from negative infinity to infinity, psi so this is the same as psi, the magnitude of psi squared. We looked at that last time. So if we integrate psi squared dx, let me just try and slow down. We get the value of, who can guess the value we have? We have the value of 1. Let me first check the so we have the value of 1. And so because we are sure that our electrode is bound within this wheel, so we are certain, unless, of course, we can't have the wave function if we don't have the electron. So if you're thinking of 0, what if we don't have the electron? Then the wave functions don't make sense, because the wave functions exist where particles exist. Now, interestingly, we can just now apply our limits I was just looking for this equation here, which C sine n pi x over L. Okay. So our wave function is C sine n pi x over L. So squaring this is quite easy. Because the sine squared becomes that. If you want to, you can use brackets to make your life a bit easier. Yeah, so just, and then what will our limits be? Our limits are definitely from 0 to L. They are not from, sorry about that, from negative infinity to positive infinity. So if we integrate that with respect to x, we should have a 1. So to integrate sine, use the double angle. So you guys can go ahead and do that. So it will be a half. Okay, cos 2x is equal to sine squared. No, sorry. Cos squared x minus sine squared x. So you convert the cos into 1 minus sine. So sine squared x is going to be a half into 1 minus cos 2x. So we're going to also integrate this from here. And we'll end up with, of course, the c squared is common. Our limits are going to be from 0 to L. So it will be x minus minus what? When you differentiate cos, you get negative sign. So if you integrate cos, you have positive sign. So let's just use alpha, which has those constants, but alpha x is equal to 1. So that's clear enough. So when sine is equal to L, right, x is equal to L, sine pi is 0. And the same happens when x is equal to 0. So that really doesn't take up a lot of our time. So we substitute for x and L. So that will be, the upper limit is L minus 0. So c squared L is equal to 1. So c is going to be equal to, there should be a 2 somewhere. Oh, yeah, there was a half here. L over 2. So C is going to be 2 over L. So C itself is root 2 over L. So we can just substitute for that, and then we get our wave function psi is going to be equal to root 2 over L sine pi nx over L. Hope I've not messed up something. So that is our final solution. That's our final solution for the normalized wave function of a particle in an infinite box or in a one-dimensional box. So we call it particle. That's the solution for particle in a one-dimensional box. And if it's an infinite well, then it can easily represent a one-dimensional well or particle in a box. Maybe so. So we'll end there. I think it is not in our intentions to keep on with this. Now, for the assignment of lasers and superconductivity, you have the guide, and so you should be communicating with the group members. The group members will need to state the contributions. So let's just have that at the end of the video. Let's scroll down. Individuals should indicate so again, there's a bit of inheritance from the previous one, so no plagiarism, that's obvious. No, can't go to one source and have your work and submit that source as your effort. Yeah. But then you're going to have a bit of a longer page, so the file limit, a bit of a longer document. I didn't put a page number, but as long as longer document, make sure you have illustrations and reference. Illustrations. And references. So those are important, and then we'll see when to schedule the presentation. So we'll meet again. Now, the presentation, you could choose to have Word and then you make a presentation. And make presentation. Or you could I wouldn't advise it though. So you could choose to have a Word document submitted and then make a presentation in PPT, or you could just choose to also submit PPT, but I prefer you make a Word document with the references, and then for your presentation, you make, that's when you submit the PPT, when you're doing the presentation. But I think I'll allow both, because you can still reference within the PPT. So yeah, it's I think it will be up to preference. Ambrose, you're in two groups because you're in two courses. If you're in two groups in the same course, I think you should indicate that. Usually people who came in late, I tried to enroll them into just one of the programs, but I figured out it might be to their disadvantage. So wait, there are no descriptions in the assignments. They should be there. Let me check Mwele, as Ogola calls it. There should be descriptions. Basically, basic operation, then applications or use cases of those lasers. So in terms of scoping, it depends. I mean, you guys could look at a number of maybe, okay, like history. So brief history, like for lasers. Principle of operation. So in the brief history, you can just mention when the effect or the when discoveries were made and key contributors to those discoveries. Then operation works mostly for lasers. Operation modes. Just operation. Then for superconductivity, you look at what is called occurrence. Conductivity. Then for both of them, you look at applications. But for superconductivity, there are types, even for lasers, types of lasers. So applications. Okay, they usually what is called state of the art or future. So this is like a bonus bit. So future applications or state of the art that becomes important. Let me just copy that. I'll put it in my text file. Yeah, so those become important. So if you have a page for history, maybe 2 pages for operation, 2 to 3 pages. This is 1 to 2 pages. So you can have somebody look at that. So 2 people, usually I'd advise that 2 people look at something and then they consolidate for the group, or 3 people look at 2 topics and then consolidate for the group, or 4 people look at 3 topics, etc. So operation occurrence is 2 to 4 pages. Types. Of lasers or superconductivity. No, 2 to 3. No. Just need to. Sorry about that. What do you want to briefly? Let me first stop some people from calling me. Yeah, so this is typical about the assignment. So 2 to 3 pages. It's not part of the lecture. Types of lasers, stroke superconductivity, that you should be guided, but less than 10. You don't want a copy and paste. So if you're to use types, let's see, for lasers, you have a certain, there are many types anyway, but depending on the groups. Let's say you have 1 type per page, maybe 5. 5 is decent. Applications, also 5 to 6. Yeah, state of the art. We should limit this to about maybe less than 4 pages. Yeah, so that is it. But again, if you think you can do this in 1 or 2 pages, that's not a big deal. This is just upper limit. So 4 plus 6 plus 10, that's about 16 pages references. So the whole thing should be less than 20 pages. All documents done. Unless you have many references, so they less. So if you have 2 pages of references, then you can be excused in the page limit. So you have a brief table of contents on 1 page, and then you can also have the cover page on the same table of contents page, but that's really up to you. But the actual content should be less than. Okay, we can modify this whole document content less than 20 pages, excluding reference. References, cover page, etc. Though I would discourage a cover page because people just have a page with text and then have the group members. Table of contents. So I think it is clear now, clear. Should we put a title here? Lasers and superconductivity assignments. Assignments. Okay, the spelling still need to be correct, but so yeah, that's what we have. The descriptions are not on Mwele. So I'll just post this to the group, I think. I'll just post this to email, and then your class reps can share that. I'll just use the thread I've been using. Apologies for, because it has everyone already. Yeah? We've been using. Let me first send this email which had the issues I sorted, and then do the assignment. So, occurrence is misspelled, but, no, where did it highlight it as misspelled? Occurrence. Behavior, unless there are questions, you can ask audibly or you can type in the chat. The deadline is soon, so I think you guys can submit. Okay, I'll need to put some other rules so that all the topics are covered. But given the brief period that we have, I think groups can only work on one thing. So, for example, I think we have to be fair to the time left. Okay, maybe I'll have to go to Muel and edit it and edit the submission. But groups should submit at least one, since now you can't belong to more than 2 groups. I'll see if I can create, I can group the groups in groups so that you can choose one topic. I don't know if you'll use heads or tails, but one, we need to make sure that the topics are covered. So you don't want, like, for example, all the groups doing superconductivity. That would be weird. So we have A to O. I don't know how many letters those are. Those are 15 groups. So you need about half of them doing lasers and the other half doing superconductivity. So groups A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Should we leave it to groups to decide? What do you guys think? So group O is the new one. So I think like A, B, C, and D can choose to have, so that you have a bit more variety. So does it help? Then E, F, G, and H, I, J, K, L, M, N, O. Let me see the requests. Yeah, the group descriptions are going to be sent to your class reps. Because I only remember the ones, I think, for telecom and biomedical. Yeah, so Haga, you'll have to convince your super group that you're doing superconductivity. So only superconductivity. Yeah, we'll have a small extension since we are coming up with the details, but okay. I will decide for you. So group A will do. Haga, which group are you in? Since you raised that bit. So you can work backwards. Okay, let's. So A1 can do lasers. Like that. So B1 will now do superconductivity. So like that, C1 will do lasers. Hmm? Okay, let me do A1 so that I make my life easier. To D1, we'll do lasers. Then E1 to G1 to H1. We'll do superconductivity. Then I1 to L1. We'll do lasers. Then M to M1 to N1. We can do superconductivity as well. So that means you need to coordinate with, so, yep. So that means there's a total of 8 times 4 is 32 participants working on one thing. Yes, so I think we should have some quality work from there. So that's the command biomedical. Let me post to the chat as well. So I'll add the description and then I'll have it sorted, but that will be later on today. So the other groups will also follow this template. I'll just need to make sure how many they are. They might be less than what? 1, 2, 3, 12, 13, 14, 15. They might be less than 15, but we'll follow the similar bits. It's just that I can't access them really now. But I'll send that as soon as I get confirmation for you, either the first 3 groups or the first 4 groups. Okay, I'm trying to log in now. Yes. Just want to go to my course. Colleges. Okay, I don't think I have to keep you guys here long. I'll just post that to email and to the discussion with the class reps. So have a good day. See you guys on Monday. Bye-bye. Let me first stop the recording. I can't stop the recording, but I don't stop the recording from here. Stop recording.